The broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome to our live data analysis using Weibull++ webinar. My name is Simon Carless, one of Weibul's business development managers focusing on reliability training, consultancy and software. I'm extremely pleased to introduce Bob Petch, one of our reliability specialists, who will be presenting the webinar today, addressing the role of live data analysis in product development, highlighting key definitions and providing a couple of examples of how it's used with the ReliaSoft Weibull++ tool. The webinar will run for about 25 minutes, at the end of which we will have a Q&A session. I want to make you aware that all attendees are currently on mute, so if you have any questions or comments, please feel free to post them directly onto the questions dialog box during the course of the webinar, and we will aim to address as many as we can at the end of the presentation. Before I hand over to Bob, I want to take a couple of minutes to summarise the Weibull Analysis portfolio. And for the benefit of those who haven't spoken to us before or aren't familiar with Weibull Analysis, we are an engineering analysis business, enabling knowledge transfer through consultancy, training and software. We are the sole distributor of the ReliaSoft suite of software in the UK, which Bob will refer to during the webinar. In addition, we also have a portfolio of other software products catered to specific industries or physics groups, and I would encourage you to visit our website, wildanalysis.co.uk, and get in touch with us regarding your engineering analysis needs. Now, over to Bob.
Okay, thanks Simon. Hi, my name is Bob Petch, and in this webinar I'll be giving a quick brief introduction to live data analysis and how it can be used as part of a reliability program. I'll start by covering some preliminary definitions for what we mean by reliability and failure, and the type of data that will be needed to perform an analysis, including some of the issues that can arise when gathering the data. I will then show how a simple analysis can be performed using ReliaSoft's Weibull++ software, giving examples of the types of results that can be obtained and how these can be used to help demonstrate reliability against a required specification. I would like to mention briefly that Weibull++ is just one of many tools within ReliaSoft's synthesis platform. Weibull++ is specifically designed to perform live data analysis, with the results stored in a common database that can then be read into subsequent analyses, such as when you're building a reliability block diagram or a fault tree within BlockSim. As part of a reliability program, it is important to give a clear definition of what is meant by reliability and also what is classed as a failure. We define reliability as the probability that an item will perform without failure under given conditions for a given period of time. Being a probability, it will take a value between 0 and 1 that will be both a function of time and use conditions. These should be understood to remove noise from the analysis. It is also necessary to have a clear definition of failure, as this can be subjective. We define failure as the termination of the ability of an item to perform a required function. These should have been discussed and agreed upon in a failure modes and effects analysis, commonly called an FMEA, prior to performing a live data analysis. It can be noted that during this presentation I'll be referring to life as varying with respect to time, as this is the most commonly used and easily measurable variable. This is not the sole method of measuring lifetimes, however. Others, such as mileage or number of cycles, are equally correct and which may be more suitable in certain applications. So what is live data analysis? The way that an item fails will change as time progresses. The frequency of failures will fall under a distribution that can be described with a statistical model such as an exponential or Weibull model. The aim of a live data analysis, therefore, is to understand what the probability of failure of a component or system is at various points in time. This can be determined based on knowing the times to failure for a discrete number of samples of a particular component, such as a light bulb or a switch. With this model known, it is possible to extrapolate and predict future performance. By giving reliability metrics such as MTBFs and the probability of failure at a point in time, we can demonstrate reliability. The frequency of failures at a given point in time is known as the failure rate, and this can increase, decrease, or remain constant with time. Combining the failure rates of individual failure modes over time gives us the familiar bathtub curve. Every product will have many different ways in which it could fail to serve its purpose. We call these failure modes. Each failure mode can have different characteristics, and what is of particular interest is how these failures develop over time. There are three main phases that failure modes fall into: wear in, random, and wear out. Taking these in turn, Firstly, a decreasing failure rate represents an issue that occurs less as time progresses. This is typical of early life issues that arise from things such as weak design, assembly errors, damaged components, poor joints and connections, dirt and contamination. Next, a constant failure rate is typical of random failures that are an indication of operating stresses, poor maintenance, operator abuse, and accidents. Finally, an increasing failure rate is a sign of wear-out failures. Where damage is accumulating and scheduled maintenance can be effective, these failures will typically occur due to weak design, wear, installation breakdown, fatigue, and corrosion. Overlaying these modes gives us the recognisable bathtub shape. Although the scale of each region very rarely matches the one shown, the overall trend is consistent. This chart shows how the ReliaSoft suite of tools can be applied throughout the reliability program, again from concept through to support phases. Weibull++ can be a useful tool to calculate and understand distributions throughout a product's development. Early on in the concept stages, it can be used to understand environmental and usage variations that will be important when creating the design specification. Then, during the design phase, baseline reliability can be determined based on the performance of similar equipment. Once a design has been developed, to verify and improve reliability, Weibull++ can be used during component, subsystem, and system testing to quantify and track improvements in reliability. Then, once the data from field becomes available, in the form of field test, maintenance plans, and warranty reports, Weibull++ can be used to further build up the knowledge base of failure behaviour. This information is useful to further develop future products and allocate warranty resources more efficiently. To perform the analysis, we need to know how long a product has operated before being unable to serve its purpose. The times to failure for a component can be taken from many different sources. Obtaining this data is usually the most difficult part of the process, particularly if there is a lot of noise present and a lot of sorting is required. Data obtained from lab tests is usually well understood and best controlled. Not only will the time of failure be known with confidence, but also the environmental conditions can be maintained as required. Warranty data, on the other hand, can be difficult to interpret, as we need to confirm how many hours have been accumulated and the mode of failure. It is usually necessary to get failed parts back for review and confirmation of the root cause. However, warranty data provides us with real use conditions and so may be a far better reflection of the failure rates that will be experienced than from improperly designed in-house tests. Ultimately, it is better to have half a dozen trusted data points from a clearly defined failure mode than hundreds of subjective selections. Ideally, we want to know the exact point in time that a unit has failed. This is called complete data and will be known if the item has been continuously monitored. In reality, though, the time of failure will not be explicitly known and will therefore be censored to some extent. This will include write-censored data, which is classed as a suspension. Here, the unit had not failed at the last point of inspection or was removed from service before failing. Next, we have interval-censored data, where a unit failed in a time frame between inspections, giving a window that failure could have occurred. Finally, we have left-censored data, which is another form of interval-censored data, in which a unit failed before its first inspection interval. Weibull++ is able to account for not only complete data, but also the full array of censored data types. There are a large number of difficulties in obtaining good quality data for analysis, especially from warranty returns. A few of these are listed here. These can be operational errors with data points not being captured or entered correctly, as well as user issues where products will be abused outside of their specified operating conditions or not reported as faulty. However, it can be noted that this noise may cause issues in understanding the expected lifetimes of a product. It may actually lead also to useful insight into other aspects of the product's life cycle and increase understanding into use profiles and administrative processes that could be improved within a business. Here, a robust failing reporting and corrective action system such as XFracas can be used to ensure that good quality data is collected. Next, I would like to show how an analysis can be performed within Weibull++. This example takes 20 light bulb samples that have been tested in a lab until failure. at which point they have been removed and not replaced. Being a lab test, the conditions have been set and maintained to reflect actual use conditions. These would include external stresses such as temperature, humidity, and vibration levels. Increasing these outside of design limits would decrease life and would form the basis of a quantitative accelerated life test. The times to failure, once recorded, have been entered into Weibull++. A mathematical model is then fitted to capture the distribution of the failures, which can then be used to predict the performance of other units. In this case, Weibull's distribution wizard will be used to help determine the most suitable model, and we can then take some metrics to demonstrate the performance of the bulbs. Increasingly, this is being demanded in the supply chain to give calculated values of mean times to failure and the probability of failures at various points in time, such as warranty periods. Here is the main view within Weibull++. On the left-hand side is the project manager, where we can organise multiple analyses within the same database file. This allows us to quickly and easily change between analyses and compare different data sets and models. Across the top is the ribbon interface, which has a dynamic toolbars that provide quick access to the main features of the software. On the right-hand side is the settings pane, which allows us to set the methodology and choose a mathematical model that will be used for the analysis. In the centre is the data sheet, where we record the times to failure for the first 20 light bulbs that have been tested. This value has been entered in hours. There is also a column that allows us to record additional details about each unit and the way that it has failed. For example, we could record which bulbs have a broken filament and which ones have broken due to a connection issue. Looking at the analysis panel, it can be seen that Weibull++ has a wide selection of distributions, and it is not always clear which is the best to use. There is an inbuilt tool called the distribution wizard that can help us choose which model has the best statistical fit. Due to the small sample size of only 20 units here, I have removed some of the more complex models. By running the wizard, we can see that the 2-parameter Weibull model comes out as the best fit. I will implement this recommendation and calculate the parameters from the data set. One of the advantages of the Weibull distribution is that we're able to gain insight into the failure behaviour based on the value of its parameters. These can be seen on the right-hand side. The beta value, also known as the shape parameter, tells us how the frequency of failures changes with time. Being greater than 1, being 1.7, we can see that the frequency of failures is increasing as time goes on, indicative of a wear-out failure. The eta value, shown below, often called the scale parameter, gives us the point in time by which 63.2% of units will be expected to have failed. These parameters can be quickly compared to other data sets. For example, if another sample of 20 bulbs from a different supplier had the same beta value, but a higher eta value, this would suggest the bulbs were failing due to the same failure mode, but that the second sample survived longer before failing, indicating that it was more reliable. These results can be displayed graphically by using the plotting tools. By plotting the data points on a log-log scale, the line of best fit through the data points forms the basis of our mathematical model, with the gradient of the slope giving the beta or shape parameter, and the intercept at 63.2% giving the scale parameter. With rank regression being used as the analysis method in this example, a visual assessment of the goodness of fit can be performed, with these data points largely falling on a straight line, indicating that the Weibull 2-parameter is a good model for this data set. Another useful plot to consider is reliability versus time, to show how the probability of survival reduces with time. From this graphic, we can see that 80% of units will be expected to survive for the first 400 hours. Then, by the time that 1600 hours has elapsed, only approximately 12% of units will be expected to still be functional. The blue line here represents the 50th percentile confidence level. That is to say that there is a 50% chance that the reliability figure quoted could be higher or lower than this. A useful way of determining how much certainty certainty we have in our results is to plot the confidence bounds. By plotting a 90% confidence interval, we can remove the top and bottom 5% of uncertainty. Now, by reading from the graph, we can say that from the analysis, there is a 95% chance, from this red line here, that 80% of units will survive to 300 hours, a 50% chance that 80% will survive to 400 hours, and a 5% chance that 80% will survive to 600 hours. There is a quick calculation panel that automatically calculates the key metrics of the analysis and displays them numerically. From here, we can calculate the mean time to failure, or MTTF. For this set of bulbs, the mean time to failure is 915 hours. Alternatively, if looking at the expected levels of failure for a given time interval, we can look at the probability of failure. If we wanted to know how many units were likely to fail by 100 hours, by using the QCP and entering a time of 100 hours, we can see that 1.7% of units will be expected to have failed at this time frame. Another useful metric when determining warranty periods is to look at what time will elapse for a given level of failures. Here, by using the B10 life, we can see that 10% of units will have failed by 281 hours. As mentioned, Weibull++ allows quick comparisons to be made between different samples and analyses. In this second folio, the results from a second batch of light bulbs from a different supplier are given, and we want to determine which model out of these two bulb samples is more reliable. Calculating the parameters with the same Weibull model, we can see that we have a very similar beta value, indicating that they are both wearing out and failing due to a similar mode. However, with this one we see a much higher eta value. In this case we've got 2050 versus 1026 from the previous samples, suggesting that this second set is actually more reliable. This can also be shown graphically by overlaying the two plots, and I can insert those here. If we again look at reliability versus time, with the first manufacturer, and so from the first data set of the line shown in blue, and the second manufacturer shown in black, the second manufacturer's bulbs can be seen to be more reliable at all points in time. This can form the basis of an objective component selection, as the cost differences of different components can be compared against their likelihood of failure for the required mission time. From here, these plots can then be exported as images, or the results exported to MS Office or stored within the ReliaSoft repository as required. That concludes the demonstration of the software, and I'd like to pass back over to Simon.
Thanks, Bob. Just before we go to the Q&A session, I'd like to make you aware of our upcoming webinars and training courses. We have a system reliability modelling webinar on the 4th of August, starting at 2 o'clock local UK time, which will be based using ReliaSoft's BlockSim software. And then with forthcoming training courses, we have 3 training courses in our diaries. Thursday 20th of August, there's an Introduction to Reliability Principles course. Monday 7th of September to Friday 11th of September, there's a Foundation of Effective FMEAs course, which is 5 days. And then from Thursday the 17th of September to Friday the 18th of September, we're hosting a focused managing and improving reliability within electronic product design course. From the website that's marked up on the screen there, you can see where we can get our full range of courses that we provide. So we look forward to seeing you at these events. Well, thank you for listening. If you have any questions or comments, please feel free to type them into the question box, and we will try and get through as many as we can in the time we have available. I've got a couple of questions here. So the first one I have here, Bob, how many samples are needed to perform an effective analysis?
Okay, it's a common question that gets asked. It's possible to perform a life data analysis using as few as 5 or 6 data points. What really matters here is what level of confidence we can have in our results. So generally, what we want to see is a trend in the data points that we do have. And as was mentioned with the lab test data versus warranty data, it's better to have a very few number of trusted data points than a large scatter of noise. But ultimately what we want to try and get to is increasing the confidence. And so if when we plot the confidence bounds, there's a big discrepancy between the upper and lower limits, then that would be reason that we would need to perhaps look into testing more units during our analysis.
Okay, well, thank you for that. Question 2, is it better to see wear in or wear out failures?
This will very much depend on the nature of the product, and it's more a reflection of how we can deal with these wear in or wear out issues. So if with wear in, if that's occurring early on, it may be necessary with electronic components, for example, that would then trigger a burn-in process to be implemented to try and reduce the number of wear-in failures that are experienced by customers by letting them surface within the manufacturing facility. Similarly with wear out, this may require some redesign if things are wearing out too quickly, or some kind of maintenance scheduling to repair any damage that has occurred before it becomes terminal.
Okay, I've got a last minute question here. What are the problems of not knowing the exact time of failure?
So this is again, it comes down to the certainty that we've got. So really, when it comes to having censored data, we've got a window in which we know that an item failed, and the wider that interval is, the wider that window, the less confidence we've got in fitting our model to it. And so again, as well as increasing the number of samples that we do have to increase confidence in our results, we also want to minimize the time uncertainty from any sensors that we've got. And this can be achieved either through monitoring the equipment with onboard diagnostics or reviewing warranty processes to ensure that faults are reported in a more timely manner.
Okay, that's clear. Okay, Bob, well, thank you for that, and thank you for listening, delegates, and we look forward to hearing from you in due course. Thank you again.